All right, hello. The purpose of this video is just to talk about the assumptions that we're making in multiple regression. So we did the same type of thing in linear regression with only one predictor. As we'll see, the assumption checking is super similar, which is really nice because if you've kind of understood what was going on when we did this in section 6, this really isn't that different. So kind of big picture, now we fit our regression model with first year GPA as the response. We've made some predictions with it. We've talked about a way that we might compare models with adjusted R squared. And now we're going to check some of these model assumptions to make sure that we can do some hypothesis tests or construct a confidence interval. And so the assumptions, as you can see, are the same as they were before. We'll see how they're like only a tiny bit different. For linearity, we're going to assume that there's a linear relationship between the response and each predictor. And so before, since we only had one predictor, we just had to check a single scatter plot because we just had the response versus that predictor. Now that we have more than one predictor, we're going to check scatter plots between the response variable and each predictor. All right, so really that's the same exact thing, except now we're checking more than one scatter plot instead of just one. For independence, we're going to assume that the error of one observation tells us nothing about the error, or tells us nothing about the errors of any of the other observations. So this is also exactly the same as it was for simple linear regression. So again, nothing new. In this case, we have 1,000 different students. There's no real reason that student one's error or residual is going to tell us or is connected in any way to the other residuals. And so we're kind of good there. For normality, we're checking whether the errors are normally distributed. And to do that, we're going to check the histogram of the residuals. So still, like totally nothing new, which is awesome. We'd have the same exact assumption, the same exact check for simple linear regression as well. For constant variance, our assumption is that the errors have the same variability for the range of values of our explanatory variables. This is the only one where our check is going to be slightly different. Remember before, take a minute to think about what we checked, which plot we checked to assess this assumption for simple linear regression. Okay, that was only 6 seconds, but maybe you paused the video. Now instead of checking a residuals versus explanatory variable plot, we're going to check a residuals versus fitted values plot, where fitted values are predictions for all observations. And so we're going to assess the plot the same exact way that we did before. So let's kind of see that in action a little bit for our SAT example. And so just for space, I've kind of omitted the other scatter plots. I'm only showing first year GPA versus math SAT score. I'm not showing the like SAT verbal score or the high school GPA just to save space. But we could see that there's no curvature in this plot. So since there's no curvature, linearity is good. I just made a note that linearity is satisfied for the other variables as well, so we're good. All right, so let's next look at our residuals versus fitted values plot. Again, that's when we're going from left to right and making sure that the spread around 0 is about the same for all of our fitted values. We can see in this plot that the spread does actually seem to decrease for higher fitted values. You could kind of see it kind of collapse inward a little bit, but we're just looking for like super strong violations of the assumption. And so that's not really that strong of a violation, so we're saying that we're good there as well. So we're saying good, residuals versus fitted plot shows about the same spread. For normality, again, we're just looking for strong violations. I've got our histogram of residuals plotted here. We're seeing some slight left skewness, but not really too bad again. So this normality is also good, though there is this slight left skew in our histogram of residuals. Finally, from these plots, we could look at whether there are any outliers. And so outliers, we're just defining have large positive or large negative residuals that would indicate that our model is predicting the response to be super different than what the observed response actually is. We see, you could look at either of these plots really. On this plot, I'm looking on the y-axis to see if there's any residuals like way up here or way down here. On this plot, I'm looking at the x-axis to see if there's any residuals like way over here or any that are extreme like way over here. Both of them look totally fine, so I'm not seeing any outliers here. Give it a little smiley face for happiness that all of our assumptions were satisfied. Okay. There's a note here about the independence assumption, and there's also another note about what we could extend our results to. So we talked way more about that issue earlier in the semester and in the middle of the semester, but we haven't talked about it recently with this regression stuff. It still applies. So if we have 1,000 students from that college, we might not want to apply what we learn here to other colleges. If we do apply it to other colleges, we have to make that assumption that those colleges are super similar to the college that we actually have data on. So that's really just a note to just say that where can we apply our results issue doesn't really go away. Finally, on this page, I'm just going to make a note about skip, and we're skipping this entire page. It's not like completely necessary, and so if there's something to cut, this is going to be it. We're not going to talk about collinearity or the effects that collinearity collinearity can have on a multiple regression analysis.